I'm currently posting a series of videos in which I'm attempting to repair and restore this HP 9845B vintage computer. In that series I've been going through this machine, repairing it as I'm going, finding a few faults here and there, failed ROMs, some failed ICs, been through the power supply and the chassis and the keyboard, and it's now up to the point where it's starting to boot up and I've got round to working on the printer. And it's given me a few headaches. I found a lot of failed parts on this. I'll go into the faults and the repair in the main series. This video is a bit of a detour, and it's something I've been wanting to do for quite a few years now. This is the control card for the printer, and at the far end of it, you probably can't see it, there's a white 40-pin device. Very interesting device. It's a microprocessor of sorts. It's the HP NANO processor, and it's a bit unusual in that it's a kind of a microprocessor that does not contain an ALU, so it can't do any mathematical functions other than comparisons. But it's extremely useful for this type of control application. It gives very high speed, flexible control. It runs code from a ROM as a normal microprocessor. But there's not a great deal of information available for it. You can get the manual for it, the original HP manual, but it doesn't contain a huge amount of information. There's a bit of information in the HP patent for this machine on the printer, but that doesn't go into too much information either. And I've encountered the nanoprocessor quite a few times in the past, and it's an interesting device. It's relatively simple. But the lack of information can make it a bit of an issue to work with. So I thought I'd try to help out with that a little bit. I've repaired, I guess, 20-25 machines that contain the nano processor, but this is the first time I've ever owned a machine that has one, and that gives me far more scope for experimentation and playing with it. So I decided to take advantage of that. And it's probably worth pointing out here that I may seem to take a very roundabout way of completing some of these repairs. It's partly to be thorough, to make sure that I don't miss anything and we end up with the best result possible, but also it's because I don't do these repairs just to end up with a working machine, which might sound a bit of an odd statement. But I do this for the enjoyment of learning how these machines work. I want to know how they work internally, how they were designed, and so quite often I like to, where possible, pull them apart, examine the inner workings, experiment and try and figure out exactly how the engineers designed them and what the thinking was behind it. And I get far more out of these repairs by doing that, and also learn more for future repairs. And this is no exception. So this video is going to be about the nano processor. And if you're not interested in that, you might want to skip the video. But what I decided to do as part of this process is make use of the fact I now have a machine with a nano processor that I can play with. So I've decided to write a nano processor simulator. It's a tool that I'll show in a few minutes that I will be using in conjunction with the logic analyzer, and it will allow me to look at the inner workings of systems that contain nanoprocessors and simulate their operation. I'll explain this more as we go through this particular video. Now this still doesn't work. I've been looking at the simulator, have done some repairs on this board already. I'll detail those in the main series. But just to help clarify what's going on in this particular video, I'll boot this up. We'll look at the logic analyzer and see what this does when we power it up. So looking at the logic analyzer, I've got the standard setup loaded that we've used previously, and I've got the trigger set to an address on the address bus of 065. This is hex numbers, of course, and the data bus of D0. I'll explain why I've used these when we start looking at the simulator. What I'll do now is arm the analyzer and we'll power up the HP. And you can see that it's triggered. I'll turn the machine off, and if we start scrolling through this, just adjust the resolution. So if you start scrolling through this, we'll see that it's capturing data, and we'll go through, it's going through incremental addresses, doing a bit of work. I'll keep going through, we end up back at 65. So it's going round, and it goes round and round this loop, and every so often it will branch off into a completely different part of code and then back. And that's the interrupt handler, so we can trigger on that. We'll try that in a minute. I know these addresses and data because I wrote a disassembler for the Nano, and I ran the code from its ROM through the disassembler, started going through that, and it was going through that that really prompted me to want to write the simulator, and we'll look at the code and the simulator in a few minutes. So as you can see, the code is just going around a tight loop. Ever so often it will branch off to a different block of code. So what I'll do is enter a different address, and I know these addresses because of course the disassembler provided the source code, and I've been going through that and commenting on it. The reason I'm putting a value into the data field is because the way that the bus is handled on the nanoprocessor means that there are interim values that often trigger the analyzer when you don't want it to. So I'm putting in the data value I expect at the address we're trying to trigger on to make sure we don't get false triggering. If I now arm the analyzer, notice we've now hit this address, and if I keep doing this, you'll notice that we are on a regular basis getting through to this address. But if I scroll through, there's not much going on in that handler, and it very quickly jumps back to the address that we first triggered on at 65, or at least that block of code. So you can see now we've gone back to that block of code, and we're going around again, and we've got back to 65. So it's just going round and round a tight loop of code from 65 up to 70 something, branching off to 1F9 at the interrupt handler on a regular basis. And you can time this, it's taking anything between about 54 and 110 microseconds between each of the interrupt branches. So what I'm going to do now is press the paper feed button on the HP, and while I'm holding that I'm going to rearm the analyzer so we jump back into this interrupt handler. So I get ready to arm the analyzer, press the button, it's now triggered. You probably heard the motor spinning on the HP. I've removed the drive belt so it doesn't keep feeding paper out. As part of the fault it's got, it just feeds out paper. So we've now jumped back into the interrupt handler, but if I now go through the interrupt handler, remember it was not really doing much previously, whereas now if we scroll across you'll see that it's doing far more than it was. So it's doing something, it's branched off to a different handler, and this goes on for quite some time, and it's quite a long time now before it goes back to the loop we were in. You can see it's gone to a completely different address. So it is something in the interrupt handler that is responding to the key press, and that's not surprising. The system and the information that is available for this is fairly minimal, but the system uses this. Let's try and bring a light in. So there's a single interrupt handler, and I don't know if you can actually see this. I'll also zoom the camera out a bit. So this is out of the patent for this particular machine, and you can see there's a single interrupt vector. In fact, there are two interrupt vectors, but one's just for a reset. And there's a selector. The register 12 is used to determine which particular handler we jump to, and these handlers are part of the control loop system. So you got this kind of control algorithm, and it jumps into different loops, and each one of these is a pass through the interrupt, and it will determine which one to jump into based on the the value in R12, in the register 12. So there are different modes that it runs in when it's in the interrupt, and that's what we're in now on the analyzer. So we need to simulate all this, but it means because of the way this runs, it's quite difficult to kind of pick your way through using just the logic analyzer. So we'll go over to the simulator and I'll try and explain why I wrote it and how it should be able to help us. So over at the PC, if I open up the source code, now this is the source code that came out of the disassembler that I showed in the previous video in the repair series. So I wrote this just so I could get access to the pseudo source code for the printer nanoprocessor. I couldn't find it available anywhere. I couldn't even find a binary image for that particular device, that particular printer. So this makes life a lot easier, and I started going through it, as you can see, using the logic analyzer, and I started commenting it. Now there are generic comments that are added by the disassembler, such as this one. But I started trying to flesh it out, figure out what each block of code was doing. So you can see this is the initialized system block of code. And if we keep going through, we can see the main idle loop. So you recall on the logic analyzer, we used an address of 0065 with a data value of D0. And that's why, it's because that's what I'd identified as the main idle loop. And this is that small loop that it was going round and round, and we saw in the logic analyzer. And then every so often it will jump to the interrupt handler. Now the interrupts on the nanoprocessor work a bit like the mode 2 interrupts on the Z80. We'll look at the schematic in a minute. And when the interrupt input is activated on the nanoprocessor, it activates or enables the interrupt acknowledge output on the processor. That is intended to allow external devices to put an interrupt vector onto the data bus that's going into the nanoprocessor, and the nanoprocessor then uses that value as a vector. In this case it results in a vector of FF. We'll look at why that is in a few minutes. So if we go through to FF, what we have here is nothing more than a small interrupt vector table. The system only uses two interrupts, or two vectors rather. One's a reset, and that's created when the init line goes low. It resets the board. It doesn't really reset it. All it really does is get it to branch to the startup address. And as long as the code has been written to allow a restart by jumping to that address, it amounts to a reset. The one we're interested in is this one, and it will jump to the actual handler, which is at 1F9, which again is why we use that address in the analyzer. So if we go through to 1F9, we can see this is the timer interrupt. I'll explain why it's the timer interrupt in a minute. And you can see it's a 1F9, and this is the code that we saw, and I used a data value of 78, and again this is why, it's to make sure that we triggered at this point. And then it starts going through the handler, uses register 12 to determine which of the individual handlers to jump to. So there are 7 in total, and we saw these in the algorithm document I showed from the patent, and there's a different loop that it will go through depending on the mode that it's in, and the mode is set by the current value in register 12, and then each of these blocks of codes will handle the particular process. And then beyond that are the helper functions and the other functions for allowing the system to operate. But the reason I decided to write this simulator now is because I was encountering blocks like this. Now if you encounter something like this in firmware, it's normally indicative of data values, data strings, and it's because some of this code is unreachable if you just try and follow it through. In the nanoprocessor it's different. It's far more likely that this is a lookup table for indirect addressing. and the indirect addressing on the nanoprocessor is a bit unusual. So for example, a particular indirect instruction, if it wants to jump, it will take the bottom bits of the instruction value, it will bitwise OR those with the bottom bits of the R0 register, and that will give you the bank offset, and then the offset within the bank is either provided by the current value in the accumulator or the next byte in memory. So trying to keep track of that on the logic analyzer is very difficult. So when I started seeing these, I decided now was the best time to write this simulator, and there are quite a few of these. If we go through, you'll find I think about 6 or 7 of these lookup tables. And the other thing with them is because of the way the nanoprocessor indexing works, they don't need to be close to the selector code. So normally when you get a lookup table, the instructions just before it are the code that determines which of the options to jump to. It's different in the nanoprocessor. These tables can be anywhere. They don't need to be anywhere near the code that actually makes use of them, which is what's happening in this case. We've got another lookup table here. If we keep going through, we'll find more examples. So when I started finding these, there's another one here, I decided that trying to follow this through with the logic analyzer would be very difficult, because I'd have to try and keep track of what's in the instruction, the R0 register, and the accumulator, or the next block, or the next byte of RAM, or ROM rather. And so it wasn't really going to be practical to do that, and you can see there's quite a few of these in here. It makes the code very complex. And for several years I wanted to look more closely at the nanoprocessor anyway, and this seemed to be a good opportunity for me to do that. So we'll get the code out of the way, and we'll have a quick look at the schematic so we know what we're aiming at. I don't know how clearly you were to see this. So we have the nanoprocessor itself. This is the schematic for the board that we looked at. There are 3 boards in total really that drive the printer. There's this one, there's the right hand riser board in the machine, and then there's the PCB in the print head itself. This is the main control board. So we have the nanoprocessor, we have its ROM, and then we have various circuits around it that we also really want to simulate if we want to simulate the process that's being run in this printer. So one of them is this arrangement, and this is the shift register for sending bits, stream data out to the print head. So we have a character ROM, looks a bit like a CRT system, where you have a character ROM and a shift register. So we need to really simulate that. We then have this timer down here, and it's a loadable 8-bit timer, and this is the interrupt timer. So the system works by loading this timer, and depending on the value it loads it with, you'll get different intervals between the interrupts, and it uses that, for example, to control the step rate of the motor, amongst other things. So we need to simulate that because it is an integral part of the way this system operates. And this is very similar, if you're familiar with something like a PIC microprocessor, this is similar to an internal timer that's set up to generate an interrupt. So when it overflows, you get an interrupt. One thing that's a bit unusual is there is an interrupt enable and an interrupt disable instruction within the nanoprocessor, but it doesn't do necessarily what you might think it does. It doesn't disable the interrupt pin. The interrupt pin is always active. The only thing it does is it enables or disables, that raises or lowers the value on the interrupt enable output pin, and you use that externally to gate the interrupt going into the device. It's really only a direct control pin. So you've got these direct control pins that are like the in-out pins on a PIC, and you've got 0 to 6, which you can control using DC commands, and then the interrupt enable and disable uses the 7th one. You could just use one of the DC lines to do exactly the same thing if you want, but then it wouldn't respond to the interrupt enable and disable command. So it's worth bearing that in mind as we go through, that we do need to look at the schematic when we're trying to figure out what the nanoprocessor is trying to do. The nanoprocessor can also access external, what they call devices, and they're not really necessarily devices, it's just a value that it puts onto these 4 lines along with a read-write output. So the read-write output is low for a read, high for a write, and the value that's put onto those 4 lines in this case is decoded by these 2 devices and the read-write line, and this determines which particular device we're trying to access, whether it's this binary input buffer, the timer, the shift register, or anything else. So keeping all this in mind, we need to simulate a few things in here. Firstly, we need to simulate the nanoprocessor itself. We need access to its code. Ideally, we need the shift register if we're going to simulate the printer. We definitely need the timer, and we need the ability to feed data into the nanoprocessor, and also we need to be able to feed in the information from these devices down here, which is the status information. So for example, when we press the paper feed button, that comes in through this device, and this is a latch that latches that information so the nanoprocessor can read it when it wants to. One other thing I wanted to simulate was the RAM. So this system uses RAM, and it doesn't use it just for buffering data, it also uses it to store process status information. And we'll probably look at that in another video, but I need to simulate this if I'm going to simulate the way that this system is running. So RAM access is controlled through this counter, and this is the address counter, so the Nano can load this with a value, and then when it tries to read or write the RAM, that process also increments or decrements the address counter, so we need to simulate that as well. So bearing all this in mind, I started writing the simulator itself, so we'll now take a look at that. Now the easiest way to write a simulator is to just use the binary source code file. I decided not to do that simply because I want to be able to use this in conjunction with the logic analyzer. So I've written here something that amounts more to an IDE. So this is the output file that we just looked at. This is what comes from the disassembler that I wrote, and it uses this code directly. It doesn't use a hidden binary copy of this. It uses this to actually do the simulation. Now it does pre-process this within the software to make the software more efficient, otherwise it would run very slowly. But it is using this directly, and you can see the highlighted line is the next instruction that's going to be carried out, and because we've just started it, it's obviously on the reset vector instruction, which is instruction at address 0. But otherwise this is the exact same file, and it makes it very readable. Not only that, but we can edit this if we want to in real time, and that gives us the ability to carry out experimentation, or even use it as a fully fledged IDE if we want to develop our own code. And off to the right here, this first box or panel is the nanoprocessor simulator itself, and this contains the internal registers, the extend register, the subroutine stack, interrupt stack, device select, direct control pins, interrupt enable pin, and the interrupt input pin, cumulative value, and the instruction pointer. At the top here we've got a timer. This just gives us the real-time time, so it tells us how long the processor would actually take to do something, because obviously this simulator runs about 100 times slower than the actual nanoprocessor processes the data itself. We've then got to the right of that the elements that I've simulated. These are really the hardware elements that are specific to the HP printer. So we've got the RAM counter that I showed on the schematic, the RAM itself, this is the contents of the RAM, the number down the left hand side is the address of the RAM, and the table on the right is the contents of the particular address. You can see at the moment, because we haven't run any code, they're empty. The devices, the reason there are 2 columns of devices is one's for input and one's for output. As I said, these aren't necessarily devices, these are really values that the system reads in or writes out in response to an in-out command. But they can be different, so I've used two columns here. This allows us to put data into the Nano when it does a read, and it allows the Nano to output data that we can then see, so we can see what it's doing. I've simulated the shift register. Again, this is what we looked at on the schematic. And also what I've done is there's an internal array into which, when we start up the software, it reads the contents of the character generator ROM. So this gives us the actual data that the printer would put out because it has access to the character generator contents. We don't really look at the contents directly, but we'll see that as we start going through the simulation. Probably look at that in a future video, but for this video I just want to duplicate what we did with the logic analyzer so that we can kind of demonstrate this is doing the same thing. We've then got the interrupt timer. So this is the number of clock cycles since the machine started up. Clock divider, one thing I didn't show on the schematic, just pull that back up, is we've got this clock divider up here that's part of the clock circuit, and it's basically a divide by 256 clock, and that feeds through, and that's what's used to advance the interrupt timer. It's reset to 0 when the system starts up, so it increments before it reads it. So the first interrupt takes about 8.5 milliseconds. Each interrupt count is about 31.25 microseconds. So although this is a 256 counter, we actually divide by 128 in this simulator because the main clock going to the processor is divided by 2. So to keep those in step, we use half the division ratio. I've also simulated the motor drive. Now the motor drive itself is a little bit unusual. I'll just pull that up on the schematic. So I don't know how much of this you can see, but the motor drive, it's a stepper motor, so it's a stepper driver. But the system here is quite clever. It uses a current controlled microstep system. So you may have seen in previous videos I've posted where I've said in machines such as paper tape punches, you need a sine drive rather than a square step system to suddenly try and move the paper tape through the paper tape punch. They use things called sine drives, and the idea is you slowly accelerate and slowly decelerate the paper tape reel because it's quite heavy. And there are various ways of doing that, and the same is true in a printer like this. Because the paper reel is quite heavy and we're using a stepper motor, if you try to just step it, you'd either get slippage of the drive system and uneven printing, or you'd just miss steps entirely. So this system, it takes two inputs. One causes this counter to count up, the other one causes a counter to count down, and then we've got an enable line coming in. So assuming that the counter's enabled, then as we count up, then we go up through the current process, so it will gradually increase the current over 8 steps, and then if we keep going it will start to decrease the current over 8 steps, so 16 steps in total, and that causes the this board to go through a complete sine drive step. So 16 microsteps gives us a full step on the motor, and it requires 12 steps per character line. So one step for each row of pixels on the printer. Quite a clever system, but again we need to take that into account when we're writing our simulator. So on our simulator, the reason that we have this total steps and this slider represents the microstep positions. There'll be 16 steps in each full step, and the total steps is the number of microsteps that we've completed so far. So what we can do now is start this running, and there's various ways we can run this. I've tried as much as possible to simulate the exact operation of the internal workings of the nanoprocessor. So I'm not trying to simulate here the outcome, I'm trying to simulate the way the nanoprocessor operates. and then the outcome should be correct, and then we can use it as a proper fault finding tool. Now the only thing that's a bit ambiguous within the software that I couldn't find an answer to, if you have an answer to this then please leave a comment. The extend register is a bit like a carry or borrow flag in a standard processor, and in the HP documentation it will say something such as, if during a particular instruction there's an overflow, this is set. What it doesn't say is whether the reverse is true. That is, if you run the same instruction twice, the first time if there's an overflow, this gets set. If you run the same instruction again, then because there's been an overflow already, the next instruction is not going to cause an overflow. So should that clear this flag? Doesn't really make that clear in the HP document, so I've made the assumption that it does clear the flag if it would not normally generate an overflow. So in other words, this is the overflow or underflow bit in the process. I'm pretty sure that's the way it would work because of the way that processors normally operate, but I'm not absolutely certain about that. You have to carry out some experimentation, but I'm fairly certain that all the rest of it operates in exactly the way that it should. So we'll start this running. You can either single step. Incidentally, all the values you can display either as hex or decimal, depending on your particular preference. So we can now single step this, and so you can see the first instruction is 5F, which is a NOP instruction, and it's stepping through the code, and you can see the code auto scrolls and it highlights the next instruction that's going to be executed at the next cycle. And you can see you can go through this, clearing various registers. The display, as much as possible, I've tried to make clear. So for example, the register values, if they've never been accessed or anything explicitly put into them since a reset, they show XX, in other words unknown. So in this case, because we've cleared registers 7 and 4, you can now see that register 4 is showing 0 rather than XX, and so is register 7. So you can single step this, but it would be fairly tedious to keep doing that, so we can just run it. We've got a speed box down here. So the speed is the number of millisecond delay between each instruction. So in this case, 1000 milliseconds means it's going to step at a rate of about 1 step per second. So if we start it running, we'll see that it's going through the code, and I've identified the first part of the code in the initialization as being RAM initialization. So it goes through the RAM and writes values to the entire RAM contents, and hopefully you can see already it's loaded the RAM counter, and it's also started writing values into the RAM. You can see down here it's writing values. So we'll stop that. And you can change the speed it runs, by the way, of course. So if we increase the speed, we'll go to 10 instructions per second. You can see it's now running much faster. And before we go much further, I want to enter a few values here to make sure the code doesn't branch off into the great blue yonder. Now, of course, this is expecting certain inputs. So what I'm going to do here is set values that I obtained using the logic analyzer and the schematic. So 143, this device 1 is the status input. We'll go back to the schematic, have a quick. So that comes from these two devices. These two devices form the status input buffer for the system. So these two 4-bit devices, different devices, but they form a single 8-bit byte. And part of that are things such as the status of the buttons, the paper feed button, for example, but also the output of the decoder from the main processor to let the Nano know if it's got some data for it to read. We'll look at that in a future video, but just bear in mind what we're looking at here is really the input from this particular pair of devices. Okay, so I've entered the value that is going to really put us into the idle loops. This is the same value that would be present if we looked at this when we were running the logic analyzer earlier. I also want to have the system halt when we get to the idle loop. So if we enter the address value, which if you recall was 0065, I also want it to halt if there's an interrupt. Probably won't be an interrupt straight away because, as I said, the interrupt timer is zeroed and I've simulated exactly what the system does, so it will start with quite a long interrupt. We've been through a few instructions here and you can see so far it's taken 34.5 microseconds. So we'll now start this running and you'll see the timer incrementing. You can see the RAM being filled with data. You can see the interrupt timer doing its thing, the clock divider's counting down. When it gets to 0, the interrupt timer will count down 1, it's just about to, and you can see it's counting down. When this gets to 0, the interrupt will be activated. This is the interrupt line down here, so this is the input pin to the interrupt and the interrupt enable output pin. You can see interrupts are enabled. The system in software did enable this, and that means if there is an interrupt, we'll jump to the interrupt vector. So we'll speed this up. This does take a while. It goes through quite a lot of steps before it gets to the idle loop. So we'll speed it up a bit. We'll go up to 100 instructions a second and up to 1,000 instructions per second. If we set this to 0, it runs at about 20,000 instructions per second, which we'll come back to later. So you can see it's going through fairly rapidly. You can see the clock cycles are going up. We're nearly at the idle loop, so we're now at the idle loop. You can see the interrupt timer has been counting down, but it's nowhere near 0 yet. And if we step through, you'll see we get exactly the same. If you want to look back at the video, you'll see that the steps we're going through here, if we single step, are exactly the same as we got on the logic analyzer. And it will keep just jumping around this until something changes. And that something can either be an interrupt, or as you can possibly see, it's looking at the input values, and these bits it's looking at are what are formed with this device 1 value, which is why I had to set a value in device 1, otherwise it would cause this to branch off, thinking a button or more than one button was pressed or that data was available. Okay, so if I start it running again, you'll see that each time round it quickly stops at the address that we've set. If we run it more slowly, you can see it's going around and it will just keep going round and round this idle loop until something changes. So I'll speed this up, you'll see it going round a bit more quickly, and then it stops. So I don't want it to keep stopping, so I'm going to clear the halt address, and now we'll just keep running around. We'll speed things up a bit, and you can see the interrupt timer is going down. To speed things up, we'll go up to full speed, and you can see this is now timing down much more quickly. At full speed it stops updating this table because it was very unpleasant when it was going at full speed. So, and as we get close to 0, I'll slow this back down. You can see now the interrupt timer is getting close to 0. When it hits 0, we should get an interrupt, and because we've got the halt on interrupt enabled, it should stop the process, which it has done. What we can now do is single step, and we should branch into an interrupt, and I've tried to simulate what the nanoprocessor does here. So what should happen is the address we're currently at should be stored in the interrupt stack. Now it's not really a stack, it's just really a single register inside the nanoprocessor. So the interrupt stack and the subroutine stacks are just two 16-bit registers inside the nanoprocessor. And they used to store the return address for either a subroutine or an interrupt. Because they're single registers, it does mean of course you can't nest either subroutines or interrupts, it's a single level. But normally for this type of operation that's fine. So we should see a value of 69 be stored in the interrupt stack. You can see the interrupt line has been set in response to the interrupt being thrown. That should be cleared when we go to the interrupt. and the current interrupt vector is set here at FF, which, if you recall, is caused by the hardware setup of the machine. So let's quickly look at why that is FF. So this is the nanoprocessor. This is the data bus. Each input to the nanoprocessor has a pull-up, so if this binary buffer goes into tri-state mode, and also if the ROM goes into tri-state mode, these lines will be floating, so the internal pull-ups on the nanoprocessor will pull them high, and that gives us the FF interrupt vector. This gate here is used for the reset vector. If you recall, the reset vector is at FD, and each interrupt vector requires 2 bytes. So we basically go up to the next available one, which is at FD from FF. This gate is enabled when the init line goes low. So if we follow this down, there's the init line down here, and that's used to turn this gate on. And that in turn generates an interrupt, and the vector that's generated is FD, and that causes the nanoprocessor to reset. So that's how the interrupt vectors are obtained by the nanoprocessor. In this case, we're using FF because we are interested in the timer interrupt. So we should see the device branch to an address of FF. We should see an address of 0069 in the interrupt stack, and the interrupt flag should be cleared. So we'll step. We have indeed branched to FF. We've got 0069 in the interrupt stack, and the interrupt flag has been cleared. Now, in the machine itself, it does not hold, halt or clear the clock divider during the interrupt. It also does not take into account the time taken to get into the interrupt. So the interrupt timing for short duration interrupt intervals is a bit hit and miss, and that is true on the hardware. In fact, on the hardware I thought it was a fault. It was saying that there should be a 64 microsecond interrupt, and it was anything between 54 and 110 microseconds. But it turned out, once I'd done this, I realised it's just the way the system operates, so it did seem to be working. So we've now gone to the interrupt vector table, and this is nothing more now than a jump to address 01F9. So if we step, we should jump to the handler itself, which we have. If you recall, the particular loop we're in, which handler is selected, is controlled using register 12. That was loaded during initialization, as we can see here, to 0. So we're going to jump through to the first handler. So if we step through, we have indeed jumped through to the first handler. But nothing's going to happen. All this will do at the moment is reload the timer. So you can see here the interrupt timer is loaded, so it has indeed been loaded with a value of 2. It's supposed to give us a nominal 64 microseconds, but as I said, it does vary quite a bit. In fact, what I'll do is I'll zero the timer. So far it's taken us just over 10 milliseconds since we started the system to get here. It's fairly quick in real time, but of course it's taken longer in our simulator. I'll reset the timer, and now we'll run again until we get to the next interrupt. And you can see it's taken around 74 microseconds. It's longer than the 64 microseconds, but as I said, that's what the actual hardware does, so it's fairly gives me some confidence it's working the way the actual hardware is. And just speed this up a bit, and if we keep running it, we'll just keep going round and round the same loop. Nothing is happening. It's going through the interrupt. All the interrupt is doing is reloading the timer, and if you recall, that's what the hardware was doing when we looked at the logic analyzer. To get it to do anything else, I had to press a button. So in that case, I pressed the paper feed button, and we can simulate that. If we look at the schematic, we can figure out which bit to change, and in this case we just need to change the input value to 159, and all I'm doing here is changing the paper feed input bit so that it's simulating me pressing the button. If we now run through to the next interrupt, notice it took longer and we've gone to a different part of the code. Let's change this back so I don't forget. So I've just released the button in effect. And what we can do now is if we step through, notice the interrupt flag is set, but the interrupt enable is disabled. So although we've got an interrupt pending, it's not going to jump straight into the interrupt. It's just going to carry on doing what it's doing to make sure we don't mess anything up. And then at this point, it's going to enable the interrupt in code. And you'll see this interrupt enable line should then be activated or checked. Has indeed checked, and so the next thing that should happen, even though it's saying that the instruction is going to jump to 03C7, it actually should jump to the interrupt vector because we've got an interrupt pending and the interrupts are enabled. And this should result in this address being pushed onto the interrupt stack. So we'll step, we have indeed jumped to the vector, we've got that address on the stack. So you can see that as far as we can tell, this is operating exactly the way the nanoprocessor would. What we can now do is jump into the handler, and once again R12 is still at 0. This is our first pass through the handler since we pressed the button. But what will happen now is when it goes through the handler, it will do something slightly different. It's going to step the motor, which is what it's supposed to do. And you'll see the motor simulation will change as well, so it will change a number of steps. And it's also changed the value in R12, so because there are 2 bytes per address, this will go up in 2s, so a value of 02 means it's going to jump to the second handler next time through, and while it's going through, it's going to step the motor. So what I'm going to do to speed things up is just get it to run up to the next interrupt. You notice here that the interrupt is much longer than it was. And what it does, and one of the reasons I did this rather than trying to use a logic analyzer, is the system has to allow time for the motor to accelerate and decelerate. So when it first starts to step it, the step intervals are longer than once it's got up to speed. And you do that, if you've ever written code to run a stepper motor, you know you have to do that. Otherwise the motor might just sit there buzzing if you try and go straight to full speed without actually turning. So it does this by having a longer interrupt first time through, and then it will go to faster interrupts later on, and you can see that in the documentation that we looked at earlier. So again, there's been an interrupt thrown, interrupt pending, so we'll now jump into the interrupt. Address 75 should be put into the interrupt stack, which it is. The interrupt's been cleared, and we'll now vector into the interrupt, but because R12 is now a value of 2, we should now select the second handler, which we have done, so it's going to jump to the second handler, and it will now effectively run through the process that's been defined by the various handlers. Now in this case, what's going to happen is it's going to keep running through the interrupts. It's going to accelerate the motor, go through various stages. It ends up at TR4 in this particular instance for stepping the paper, and it will go through and it will microstep the motor, and it will keep doing that until the number of steps requested has been completed, and that value is stored in R7, in this case a value of BC in hex. So it will keep stepping now until that value goes down to 0. So rather than, and it takes quite a long time, it takes something like I think 50 milliseconds. So we'll 0 the timer. So we've just completed the first steps, and we'll run this through now until R7 gets down to 0. And because this takes quite a long time, I'm going to disable the interrupts. We don't want to keep stopping every time there's an interrupt. I'll stop on the first one so you can see that the interrupt timer is indeed shorter than it was for the first step. So we'll just run through the first one. So you see it's a much shorter step time than we had the first time through. Notice that R7 has gone down by 1, so it's counted that step off, and also the motor has moved. So we'll run this at full speed, and one advantage again with having something like this, it gives you much more clarity and vision over what's going on. You can see the values changing in real time, and it gives you a very good clue as to what's actually going on within the system. So I'm going to turn halt on interrupt off. I'm also going to speed up the system, and so when I start it running, you'll see the motor steps increasing and the micro step slider moving. It'll run very quickly, so you won't be able to read too much of what's going on with some of the numbers, but you should see R7 counting down. So we'll start this running, and indeed R7 is counting down. It's running about 20,000 instructions per second at the moment. You can see the motor is turning, so you see the slider, micro step slider moving, the steps moving across, and each one of these is one full step of the motor. So R7 is going down. It will keep running now until R7 gets down to 0. If you look at the source code listing, you notice that I identified R7 as being the required step count. That's also indicated in the HP document, so it does tend to confirm what we found. As we get close to 0, I'll slow the simulator down, and we'll demonstrate that the system also decelerates the motor. So we're getting fairly close to that. So R7's at 32. Hopefully you can see this on your screen. There is a limitation of the video resolution, of course. And we'll slow this down as we get towards 0. It's currently at 15. Okay, so I've got halt and interrupt re-enabled. So when we go through this loop, notice that the interrupt is now much longer again, because we're getting towards the end of the motor run, and it's checked to see that R7 is nearly at 0, and so it's using a longer interrupt to allow the motor time to decelerate so it doesn't overshoot the position that's requested. So when this gets down to 0, we'll get another interrupt, and then there'll be one more step, and we will have completed the motor drive task. So we're getting close to 0, and we have indeed created an interrupt. R7's at 2. If we run it again, we get an interrupt. R7 is 0, and notice the total number of steps is C0. It's 192 in decimal. And if we divide that by 16, which is how many microsteps per step there are, we get a value of 12. If you recall, that's how many motor steps are required for each row of characters. 1 step per line of pixels. So it does appear this system is working exactly how it's supposed to. Incidentally, if we now just run this, it will just now keep going round the idle loop again, because it's completed its task. It's stepped the motor, driven the paper out one line, and so it's back into its idle mode. So what I can do now is, I won't do it in this video. If you want to see more of this, then please leave a comment. You might be finding this tedious, in which case leave a comment as well. But the idea of this is I can now use this in conjunction with the logic analyzer to allow me to focus on particular parts of the system. I can figure out what values to feed into this. For example, I can feed in data values to simulate sending data from the HP to the printer, set the appropriate flags, and see what the software does. And then I can compare that with what the actual machine is doing, and hopefully this should enable me to track down the faults very quickly. And because this is an exact simulation of the nanoprocessor, it should make it very easy to track down even subtle faults. One other thing we can do, if we allow editing, is we can actually edit this code. So I won't edit this particular file. I'll close this one. I'll open a test one. So we've got a test program loaded, and what we can do now is enable editing, and this is really now an IDE. You can use this to develop code, so you can now edit what's in here. So let's run through as it is to start with, and you'll notice that one of the first instructions is to load a value of 1F into R0. So if we step through, notice we've got 1F in R0. But what we can do is change that. Let's say we want to change that to 2F. And because this system is taking the code from the actual, it does pre-process it, but it runs what's here. It doesn't run a separate binary file. So I'll just save this, cause it to reset. And if we now step through, notice we've got 2F rather than 1F. It's cleared, the reset cleared all the values, by the way. If we now step through this, notice we're now getting 2F in the R0 register. So you can edit this, and again that will make it very easy to try various things. If we think there's a particular fault caused by a particular value, we can simulate that, or we can even use this to develop our own code or to develop test programs if we want to run some test code in the nanoprocessor. So a very powerful system, and hopefully you found this of some interest.